In this video, we'll now start using the facts that we established from the previous video. So I'll keep flipping back to that front page, and I strongly recommend that you keep close access to that front page. It's a pretty concise spot. There's a lot of facts on that one page, but it's a pretty concise spot that we can keep coming back to for pretty much anything that we need to know in this initial section. Like I said, everybody, mostly as I go through these problems, I will remind you at the end, there's only about 2 of these that'll really come up for us as far as a test or a quiz. We're going to need to get used to this stuff so we can do the later stuff. Okay? So, let's start off with a fairly nice one. Oh, I also should have pointed out in the previous video, I think I mentioned it, you are going to need a calculator for some of these sections. And if you're a little unfamiliar, you could always send me little quick emails. I could show you with the calculators I have. I'll do a little bit of that in this video, try and give you a few pointers. But certainly if you're having any trouble, let me know and we could work it out. But this first one, let's start off with a nice simple problem. You are given this right triangle. We are given that this angle is 29 degrees, and we are also given that this side is 4.1 and this is x. And our directions say, find x, round to the nearest tenth. The first thing I want to establish when we start doing these problems is to pay specific attention to the directions. It gives away a lot of information. That if you are being told to round off, that is a clear indicator that the book or myself is expecting you to use your calculator. If it says something about exact values, now it's expecting us to get our answers from maybe right triangles, maybe the reference angle chart. So we'll see that coming up. But that's a big hint to use your calculator in some capacity. But just because we're using our calculator doesn't make this an easy problem. We look at a right triangle, we realize we've got all these right triangle facts on the previous page, but what are we trying to do? And let me start off with something that's not correct. People think, let's apply Pythagorean Theorem. And people do things like 4.1 squared plus x squared equals 29 squared. They put the 29 in various places, but realize that makes no sense. Pythagorean Theorem only applies when you're looking at all 3 sides. We don't know anything about this side. We don't care about this side. We're trying to find this side, the x. So how are we going to figure this out? We're going to look at what information we have. We know this angle. You could go up here. We could play some games knowing that this is 29 and this is 90. We could figure out this angle, but that really doesn't help in the grand scheme of the problem. It just opens up more possibilities, but you're taking a long way around. So let's stick with this 29 degrees. I know this is 29. I have the opposite side. I want the adjacent side. Let's take the information we have here and think of it in terms of this right triangle setup. So we know theta is 29. We know the opposite is 4.1. The adjacent is x. Which trig function uses all 3 of these? Well, they all use theta, so it's really what 2 sides are in play here. We're talking about opposite and adjacent. We're going to use tangent. We know tan of theta is opposite over adjacent. We'll fill in what we know. We know theta is 29, so I'll get tan of 29 equals O is 4.1 and A is the x. And now I will solve. Now, a lot of people go for the calculator right off the bat, but I think it's a little better here because if we're using the calculator, we should expect ugly, messy answers. So expecting that we're going to round, why don't we save the rounding for the very end of the problem? So let's just do a little work algebraically first. Treat this like it's over 1. If I want to solve for x, I'll cross multiply. X times tangent of 29 equals 1 times 4.1, which is just 4.1. Now, we typically write things like, x times 4 would be 4x, but it's a little more traditional to put the trig part at the end. But that's still being multiplied by x, so I'll divide both sides by tan 29. That isolates my x, and now I'll finally reach for my calculator. But one quick thing, whatever calculator you have, I'll show you first on my graphing calculator and then show you on a scientific calculator. Again, you may not have the exact same calculators I have, but you have similar things to look for. Just before I do any numerical work, find your mode button. If you have a graphing calculator, find your mode and look at the third option down, radian or degree. Before you do anything with trigs and angles, make sure you're in the appropriate mode. We'll do a lot with degrees, so I'm going to leave my calculator. I'm already in degrees, so now I can quit and I can get to work. 4.1 divided by, there's my tan button. Notice it opened a parenthesis. Not all calculators do that, but a lot of them. 29. Good habit, close your parenthesis. And now we can get our answer and round. We're rounding to the nearest tenth, so we'll look at the hundredths place. 5 or bigger, round up. 4 or below, round down. This will be 7.4. If I knew any units in this problem, if this was 4.1 feet, then this would also be measured in feet. If this was 4.1 inches, then this would be 7.4 inches. The units would stay the same, or whatever they are. This generic problem, we had no units. That would be our answer. Now, let's move right into a second one. Similar situation. Oh, I'm sorry. Very quickly, let me show you the other calculator. Just to realize here, a lot of these calculators, they show you your mode as soon as you open your screen. So this is already in degree mode. If you need to change this DRG button, that is my degree, and I could switch to radians if necessary. There is another unit that's gradients technically. We won't touch that. So I'm already in degrees, and same thing here. 4.1 divided by tan of 29. And of course, we get the same answer. Okay. But now let me switch it up a little bit. Problem number 2, I'm still going to give you a right triangle. Just changing my picture a little bit. I'm giving this to you, so now that is your right angle up here. I'm going to stick a theta in this corner, and I'm going to give you this value is 16.8, and this value is 21.3. And now I'm going to say find theta, round to the nearest degree. Okay? It still feels similar. But notice, in this problem, we knew the angle, and we knew one side and wanted the other. In this one, I know two sides. I could use Pythagorean Theorem to get this third side, but that doesn't get me any closer to answering this question. This question doesn't say find this side. There's no x over here. It's asking us to find theta. So now, well, what trig functions are in play here? What is it that we know? What is it that we want to do? Well, we know from this perspective, this would be the opposite side, right? Theta here, that would be the opposite. This is across, so this would be from the right angle, so this would be the hypotenuse. Want theta, know the opposite in hypotenuse. Now sine is going to be involved. Sine will be the trig function that connects these three. But now it's just slightly different. Now we'll get sine of theta, opposite, over hypotenuse. But now when I solve, this is just a little thing to remember. We'll talk more about the inverse trig functions a lot later on, but just to realize when you're looking at your calculator that you have your regular sine, cosine, tangent, but then right above it, that's that inverse notation we've seen before, and that's exactly when the inverses get used. The regular trig buttons are used when you know the angle, but when you want the angle, you use the inverse. I don't have to do any arithmetic. I mean, I could divide this, and that won't be too awful, but I'm just going to do it all on my calculator. Theta is inverse sine of all of this inside parentheses. And again, I want this in degrees. If you were in radian mode, for instance, and use this button, your answer would be a measure in radians. But we want in degrees, so make sure in degree mode. And that's it. Doesn't matter which calculator I use. I've got it set up. I'm going to use second, I'm sorry, let me slide up so you can see, second sine, and notice how now I got the sine inverse that came up. It again opened a parenthesis, and I could do all that division inside the parentheses. Don't close the parenthesis here. The calculator will think you're just doing sine inverse of 16.8 and then dividing by 21.3. The 21.3 has to be divided before we apply the sine inverse. 52.0, so that would be to the nearest degree. I'm not doing to the 10th. To the nearest 10th of a degree, I get 52.1, but to the nearest degree, that would just be 52 degrees. So both of these are nice. We're getting a little introduction to the calculator, and I could just simply say, what is tangent of 31, give you all the work, but now I'm already giving you a problem that's asking you to use your calculator in the middle of another problem. So these are nice, but this last one, this really gives us the type of problem that we can expect on a test or a quiz. Not just being handed a right triangle and being asked to find something, but looking at a word problem. There are a lot of right triangle situations that naturally show themselves when we start looking at, when we start drawing out a picture. There are a lot of right triangle situations that come up. So let's take a little look. Let's see what we have here. Let's say you are standing at a distance from the front door of a 250-foot tall building. If the angle of elevation from your shoe to the top of the building is 72 degrees, to the nearest foot how far away from the front door are you standing? We read all of this, and I'm just going to do a little work up here. I'm a little short down here. I don't want to change the page, so I'll just do a little work up here, and I'll finish down here. So just coming up here, we read through everything. Okay, let's see what we have here. There you are. You're standing a distance from the front of a 250-foot tall building. There's your building, and it's 250 feet tall. Natural ideas, everybody. This is where we start to get a little bit of those assumptions that often come up in word problems in math. We're assuming, without any extra explanation, we would assume that you're standing on flat ground so that the building is a right angle from the sidewalk. We don't intentionally build buildings that lean, right? We would intentionally build a building that goes directly up, whether it's a building or it's a telephone pole or a flagpole or anything like that. Trees basically grow straight up like that. We can assume that is a right angle. Let's keep going here. If the angle of elevation from your shoe to the top of the building, let me draw a little line there. There's the line that represents your shoe to the top of the building. The angle of elevation from here to here is 72 degrees. So that 72 sneaks into that corner. To the nearest foot, there's rounding directions. We're going to have to round. We are going to need our calculator for this, and we're going to round to the nearest whole foot. How far are you from the front door? Here you are. Here's the front door. That is the X we are looking for in this problem. So if you notice, this problem is pretty similar to what we just had up here a moment ago. We had to draw it, we had to get ourselves positioned, and as we do more of these problems, what sides do we know? How do we solve? There's a whole bunch. This one works out very similar to what we had here. I've got my setup here. I've got this side, which would be the opposite from the angle. I want this side, which would be the adjacent. So I would use tangent. I know the angle is 72. And I would solve this equation. Almost the exact same way I did here. Now, this is only one problem. I don't want you to think tangent is always what comes up. Here, just because we found an angle, no big deal, we had to use sine. We had to think of this separately. If I knew this side and wanted to know how far your foot is from the top of the building, you'd want this to be your x. Now we'd have opposite and hypotenuse, so we'd be talking about the sine function. If I knew how far I was from the front door and wanted to know this, there's just all these different possibilities. So again, we have to read each of these separately and see what happens. But now that we got this set up, same idea. I cross multiply. I didn't get to pick this. The x ended up in the denominator. If the x ended up in the numerator, that would be a little bit easier. But in the end, when all's said and done, I will end up having 250 divided by tan of 72. So to the nearest whole foot, 81.2 would be rounded off. You're standing 81 feet. Sorry, here we go. Do that division, and your answer is 81.2, so we'd round off to 81 feet. I'm perfectly fine stopping that. You could write a whole sentence, you are 81 feet from the front door, but that's perfectly fine. So again, everybody, a good problem. Definitely can do some more if you need to. Just a lot of just making sure when you set your picture up, what sides do we know, what sides do we want, get your angles filled in appropriately, and use the appropriate. I can't say it again. That's just a coincidence that both of these were tangent. Here we had a sine. We could easily do more problems and see cosine and sine come up just as often. You will notice, though, there would be no good reason to use the reciprocal three trigs here. That really doesn't help. It's better to stay with the primary. Technically, you can, again, use all these relationships. I could have used cotangent, but notice you don't have a cotangent button on the calculator. So again, another reason, stick to the primary three. Let's move along. And let's get some more problems. The next several problems, this is page 2, we are going to find exact values for all trig functions at theta. And I'm going to start really super light with one and then quickly build up to a few harder ones. So in a first quick problem, let's start off. You are given sine of theta equals 3/5. You want to evaluate all the trig functions at theta. Well, you already have one of them, but how the heck are you supposed to get the others? Well, we start work, okay? You are given this information first. And one of the keys, one of the first things to realize is that truly, once you know one trig value, you know the others. I know sine of theta is 3/5, so I'm going to work a little backwards. I'm going to make a right triangle that satisfies this information. But when I say make a right triangle, again, I really just need it for my reference. So I'm going to draw that simple one. I'm going to put the theta in the corner. I'm a creature of habit. So again, when I get the option, I'll always make this basic triangle, right angle here. So my hypotenuse, my opposite, and my adjacent with this theta in this corner. But what do I know? Well, sine of theta is equal to opposite over hypotenuse. So therefore, the opposite side must be 3, and the hypotenuse side must be 5. Do we see how that works? It's nothing special about sine. If I knew cosine was 3 over 5, the 3 would have gone down here for the adjacent, and the hypotenuse would have been 5. I could have worked this in any way. But I am going to need the other side. So we keep mentioning Pythagorean theorem, not the Pythagorean trig identity, but the actual Pythagorean theorem. Now we're going to need it. And realize it is so tempting. I cannot tell you how often people do things like this. Just whatever two sides they know equals the unknown side squared. But that's not Pythagorean theorem. When we use Pythagorean theorem, it's always got to be the hypotenuse that's the side by itself. So 3 squared plus blank squared equals 5 squared. You could swap these two. That's the only option. Now we solve. Some of you will notice there are some nice relationships. This will actually be what some people refer to as a Pythagorean triple, but we don't always get such perfect relationships. So we'll solve here. I get 9 plus blank squared equals 25. Subtract the 9, blank squared equals 16. Technically, when I solve this, I take the square root, so I would get plus or minus 4. But I'm going to strongly advocate only ever use positive values on your triangles. Think of it as distance. So -4 as a distance doesn't make any sense. That's the reason I'm only taking the positive 4. But now we're off and running. Now we've got the whole triangle. So cosine, I'm just running off these facts, everybody. Cosine is adjacent over hypotenuse. So adjacent over hypotenuse would be 4 over 5. Know yourself, everybody. If you need to spell it out, 3 is O, 4 is A, 5 is H. If you're not super familiar with these, the way to memorize these is to keep writing it out. Don't just write the answer. Write A over H. Remind yourself in the problem, in your notes, where that's coming from. Tangent of theta is opposite over adjacent. So opposite over adjacent, 3 over 4. Cosecant of theta is 1 over sine. So I get 1 over 3/5. And anytime you do 1 over a fraction, your fraction just flips. I get 5 over 3. Secant of theta. I don't want to go too low, so I'm just going to come up here to finish. But I'm still doing the same order that I established. So that I did cosecant, went with sine. Next, I'll look at secant. Takes me back to cosine. 1 over 4/5 would equal 5 over 4. And last, cotangent, 1 over tangent, 1 over 3/4 would be 4/3. Let's keep going. Nice problem. But to be truly honest, that problem is actually slightly incomplete. This is a good problem to remind people how these trig identities, how these definitions all kind of overlap. So again, knowing one value really tells you that you know them all. But this next problem is going to be more of a better full problem. There was something a little bit missing here, because technically we didn't know anything about this angle theta. So in this next one, let's add just a little bit more. Given cosine of theta is negative radical 7 over 4, and tangent of theta is greater than 0. Now, let's find exact values for all trig functions. Go backwards for one moment, everybody. There are people who are good with their calculator, and they think, well, why did you go through the right triangle? Why don't you just solve for theta, and then you could use calculators to get these other values? The issues come up with rounding, everybody. These are at least nice enough that as decimals, that's 0.6, 0.8, 0.75. But even here, that would be 1.66666 forever. So the calculator's still a little limited. 1.666 forever, you're going to have to round off somewhere, and now you no longer have an exact value. So again, it's good habits. This is establishing why we need to know the right triangle facts and starting to realize calculators sometimes leave us a little short. But now this next problem seems similar. Given these, and again, so let's evaluate all the trig. And again, I'll include exact values only. And now we realize that we're getting the extra piece. Here we treated theta like it was just a nice number, but we didn't know that. And when I say nice, that it was in the first quadrant, so that everything worked out positive. But even right here, the value I gave you for cosine is already negative. We need to realize we're not in the first quadrant. So the big picture here is figure out what quadrant we're in. That's how we're going to figure out the plus or minuses. We'll either use the unit circle concepts or we'll use the ASTC ideas that we had down here. That's how we'll know the plus or minuses, and we'll use the right triangle as well to get the values. So let's do that. Cosine is negative, tangent is greater than 0 is really telling me tangent is positive. So, again, most people use the ASTC. Cosine is negative, puts me in one of these two quadrants. I don't know which one. Cosine is negative in the second because sine is the only one that's positive. Cosine is also negative in the third because tangent is the only one that's positive. So I have two possibilities for cosine being negative, quadrant 2 and quadrant 3. But I also know tangent is positive. Well, tangent is positive in quadrants 1 and quadrants 3. 3 match both. Tangent was positive and cosine was negative. I know theta is in the third quadrant. I don't draw my right triangle in the third quadrant. I'll just remember that. And again, I'll use that for my plus and minus signs. So theta is in the third quadrant. And now I'll draw my right triangle. And again, I get to draw it, so I keep drawing the same one. Theta in the corner, there's my right angle. The negative has served its purpose, everybody. So when you're setting it up, it's a bad habit to put a negative radical 7 here. It's better just to say the adjacent side is the radical 7, the hypotenuse is the 4, and now we'll get this this opposite side, more Pythagorean theorem. Again, this is why the negatives get people in trouble. Technically, if you square this, squaring a negative will make it a positive, but that's a very common mistake for people. That's one of the many reasons why I encourage you to just keep this side positive. Okay? So I want this side, so I will get the opposite side squared plus the adjacent squared equals the hypotenuse squared. This one still works out pretty nicely. Squaring a square root, that just becomes a 7. Technically, you could say that's square root of 49, but then you could clean that up. And that's 16. Subtract the 7 over. If this wasn't a perfect square, like if I ended up here with question mark squared equals 5, I wouldn't want my calculator for the square root of 5. I would just leave it as the square root of 5. But this one, the square root of 9, is so clean, so I definitely take advantage. That gives me the opposite side is 3. And now getting my trig values. Sine of theta, well, I'm in the third quadrant. Sine is negative in the third quadrant. So I get a negative. Negative what? Opposite over hypotenuse, negative 3/4. We already had cosine, so I could rewrite it. And by the way, some people like to do it anyway. Even though it was here, they just want to confirm that they did everything correctly. So third quadrant, cosine is negative. Negative what? Adjacent over hypotenuse. They like the feeling of verifying what they had here to kind of know they're on the right track. Tangent. Well, tangent is positive in the third quadrant. Again, I keep coming back to this. So tangent is positive in the third quadrant. I should point out, I could have just used the x and y's here from the unit circle. But a lot of people like the ASTC. You don't have to highlight the plus. Again, I just like to do it to remind myself that I didn't forget. Okay? Positive what? Well, now I will get opposite over adjacent. That'll be 3 over the square root of 7. To be perfectly honest, guys, I don't mind if you leave your answer like that. The book loves to rationalize, though. It doesn't like leaving radicals in the denominator. So it multiplies top and bottom by that radical 7. You can't do anything with the top. 3 times rad 7 is 3 rad 7. That's as good as it gets. But rad 7 is rad 49, or just the radical cancels and you get 7. That's only the primary 3. I still need the other 3. But now all I'm doing is flipping. Pluses and minuses, when you do 1 over, they don't change. So when I do cosecant, it's 1 over this. So I get negative 4/3. When I do secant of theta, it's 1 over this. So I get negative 4 over radical 7, which just like this, the book would rationalize like that. And then finally, cotangent of theta, we flip this. Here, if you flip something you already had to rationalize, you're going to put that radical back in the bottom. So you could rationalize it again, but just go back to the original. 3 over radical 7 was correct, so cotangent is just radical 7 over 3. This was negative, flip it, still negative. This was negative, you do 1 over, still negative. Even after you rationalize, this was positive, you do 1 over, still positive. Okay. One more problem like this, and then we still have more to cover, but we're getting through just about everything we need from our basic set of problems. So problem number 3, given theta goes through the point -5, 12 on its terminal side, and let's evaluate all the trig at theta. And one more time, exact values. Now this looks completely different than the previous two. Gave you a trig value. Oh, by the way, go back to number 2. This is not a test problem at this stage, but this one is. This combines so many of these basic facts that this is still definitely a test problem on its own, not to mention how many times we're going to need aspects. We may not need all the trig values. We may just need one. We may just need sine. We may just need cosecant. But if we can get all of them, then we could always just find just the 1 or 2 that we need. But now we get to this last one, and all this really seems to have in common, they keep asking us to find all the trig values at theta, and they keep asking us for exact values, but now we're getting completely different startup information. But think about what this is telling me. Theta goes through this on its terminal side. Well, it always starts here, -5, 12, 5 to the left, up 12 would be somewhere up here. So theta goes through this point. So this actually represents angle theta, but now we can clearly see we are in the second quadrant. Here we had to use trig facts to figure that out. Here we just plotted the xy pair and can see where that terminal side of the line. Again, it goes through this point. It doesn't stop here, but that'll be good enough. Now I'll use the fact that we're in the second quadrant to figure out the plus or minuses. How am I going to get the values? I'm going to make a right triangle. But unlike the previous two, where I could just make a right triangle wherever I want, now I'm really going to take advantage of this picture. I'm going to make a right triangle in the xy axis, and I said that in the note page, that always happens by making the right angle going to the x-axis. In the original one, I had that here. If I was down here in the third quadrant, I'd make this. If I was in the fourth quadrant, I would make this. I always make my right triangle by getting the right angle going to the x-axis, never to the y. And now we get what we call a reference angle. This is theta out here, but we're going to use this as the angle that determines opposite adjacent, and my hypotenuse is up here. And very similar to that idea of the unit circle. How do I fill in these values? Well, look at the point. How did you get to -5, 12? You started by going 5 units to the left. So this side, the adjacent side in this picture, would have a value of 5. Notice one more time, just like up here, I'm not putting a negative on the triangle. I really think that leads to a lot of common mistakes. So I'm just using this as distance. So I went 5 units. Again, I'll get the negative from the fact that I'm in the second quadrant, not from the value itself. So that side is 5. I went 5 units this way. Then I went up 12 units. So this side, which is the opposite in this picture, will have a length of 12. And I have to find the hypotenuse. Now it's finally the hypotenuse, which is the unknown side. So that's the side that's by itself. Do a little arithmetic, you get a 25, you get a 144, that'll give you a 169, and that, believe it or not, is a perfect square. Again, we've seen it may not always happen that way, but since the square root of 169 is perfect, we definitely want to get that the hypotenuse is 13. And now we did all the hard parts, we're off and running. All the trig values, well, I'll start with sine. I'm in the second quadrant, sine is positive. Positive what? Opposite over hypotenuse, positive 12 over 13. Cosine of theta. Well, I'm in the second quadrant. Cosine is negative. Negative what? Adjacent over hypotenuse, negative 5 over 13. tangent of theta. One more time, everybody, notice. Even every once in a while, people may abbreviate and just say sine equals, cosine equals. But when you write, notice, I'm not just writing sin equals, you got to include the angle. If you don't include the angle here, you're misleading your audience. If you just wrote generically sin of blank, you lead people into thinking this is the angle you care about, so this is the opposite and this is the adjacent. So again, be careful here, everybody. Realize the notation is important. You need to include the angle with the trig function. But now back to what we've been doing. Tangent, well, second quadrant, tangent is negative. Remember, how did I get that? Right here. Sine was the only one that was positive. Cosine and tangent were both negative. So that's how I got the plus or minuses, and now the sides to get the values. Tangent, opposite over adjacent, I get negative 12 over 5. And now the reciprocals. Cosecant of theta is 1 over sine, so I'll get 1 over 12 over 13, which is 13 over 12. Secant of theta, 1 over cosine, so 1 over negative 5 over 13 is negative 13 over 5. And last, cotangent, 1 over tangent, 1 over negative 12 over 5 would give me negative 5 over 12. One more, everybody. Now we got to start talking about some values. And now I know you could say, what does he mean? We've already found a lot of values, but just super fast to look back. All of these problems, we found exact values for theta, but we never found out what theta was. And we didn't care what theta was. All the right triangle work, doesn't matter if theta is a nice whole number, an ugly decimal, doesn't matter, we never had to find it. But now we want to start looking at how do we know how to find trig values when we do know what the angle theta is. That'll be this last page. So let's start off, evaluate the following. Again, exact answers. We won't be using the right triangles anymore. I hope you already noticed we used a lot of right triangle facts. We used a couple of the unit circle facts. Whether you looked at the ASTC or you looked at the unit circle, that came up. The big thing we haven't used so far is this chart down here. And that's what we're getting into, everybody. So let's start nice. Evaluate the following, exact answers only. Let's start super simple. Number 1, cosine of 30 degrees. If you pull out your calculator, this is what I keep talking about. If you pull out your calculator and say, oh, that's easy, cosine 30, hit enter, that's not an exact answer. That's an ugly decimal. It keeps going on. You're going to round off somewhere, making it an approximate, a rounded value, not an exact. So what do? We realize that's not the key. We already saw that first page, any rounding directions were really the key to using the calculator. Exact answers, we've got a better way. And in this one, this value is literally coming right off the chart. Cosine of 30 is rad 3 over 2. We're done. Okay, let's keep going. Number 2. We're going to do several of these. These, again, some people are very familiar, others a little more practice to get used to it. So let's keep going. Next one, let's look at sine of pi over 4. Now, I didn't tell you this was degrees, but the degree symbol was there. I'm not telling you this is radians, but go back to the angle video. The angle part, the pi part of the angle should be giving that away, that that's radians. So, 2 options. If you embrace the radians on your chart, you're done. It's just like the previous one. Sine of pi over 4, sine of pi over 4 takes me right here. Just like cosine of 30 took me right here. I'm just using the radian values on top instead of the degree values. So that works. That's rad 2 over 2. But as I keep saying, if you know you're not going into calculus and you realize that radians just for some reason trick people, they feel uncomfortable, make the conversion. Pi is 180, 180 divided by 4, you'd end up with 45, but just realize you didn't do any work for the problem. You just basically retranslated the problem. You put it in different context, The sine part is still there, but now you're just looking at a degree measurement. And again, we're in the same spot. Sine of 45, there's my rad 2 over 2. Same answer. So, still easy. Let's take it a little deeper, okay? Number 3, let's do 2 aspects. Now, let's start with this. Let's look at cosine of 150 degrees. Now, you can't just look at the chart. You can't just say, oh, what to do? My chart only goes 0, 30, 45, 60, 90. But that's the idea of being a reference angle. And we saw this in that very last problem when theta went through the terminal point. A reference angle is just the angle to the x-axis. So what we need to do here, we need to realize the big difference between this problem and this problem is just that 150, oh, I still want to give you the degrees. But even if I didn't put it though, we still need to just realize that general statement, without having the pi, we should assume that one is in degrees. But the biggest difference is that we're not in the first quadrant. So not being in the first quadrant, well, what quadrant are we in? 150 is bigger than 90, less than 180, so we're over here. Again, everybody, I'm not trying to draw this to scale. 150 would be much closer to this side than this side, but all I need to do is basically just get something for reference. That if that is 150, that I'm in the second quadrant, well, cosine is negative in the second quadrant. But negative what? I need the reference angle. So if this is the standard angle 150, and realize if I kept going to here, that would be 180. So using good reasoning, that means this gap has to be 30 degrees. The 180 plus the 30 gives you 180, or 180 minus the 150 gives you the 30 we were looking for. We were short of 180, so we did 180 minus the 150 to get the 30. So the negative, because I'm in the second quadrant, and now the fact that the reference angle is 30, back to cosine of 30 takes me to rad 3 over 2. So a similar answer to what I had in number 1, but the negative, they had the same reference angle, but this one also had a negative as part of its answer because of the second quadrant. Cosine is negative in the second quadrant. Okay, let's keep going. Let's just keep rolling along. We're going to get several of these. Number 4, let's look at sine of, actually, I'm sorry. Let's do this next one. Let's do tangent of 135. The first few were all sine and cosine. So now once you start getting outside of those, you kind of have a couple of options where to begin. For me, the first thing I'm always going to do, well, 2 things. I always want to make sure my angle is standard, so that's between 0 and 360 for degrees. And then I'm always going to think about making my trig functions in terms of the appropriate sine and cosine. Tangent is sine over cosine. And when you do this kind of a breakdown, the angle never changes. So it's sine of 135 over cosine of 135. This problem is basically breaking down into 2 of these problems. But it's the same angle. 135, again, bigger than 90, smaller than 180. So again, I'm in the second quadrant. Well, sine is positive in the second quadrant. Cosine is negative. And if this is 135, I'll figure out that the reference angle is then 45. And then I'll go to my chart. Sine of 45 is rad 2 over 2. So I'll get positive rad 2 over 2 for the sine of 135. Cosine of 45, coincidence, also happens to be rad 2 over 2. But now I'll get negative rad 2 over 2 because of the negative from the second quadrant. And now we'll clean this up. A positive divided by negative is a negative. And these happen to be dividing by the same thing. So we get a final answer of negative 1. Let's keep going, everybody. Let's now take a look at number 5. And let's look at cosecant of 5 pi over 3. I've hit you with a few different things here. Number 1, that is in radians. And secondly, that's not a sine or a cosine. So again, a couple of options here. I will come back and show you how to do this in radians in just a moment. This one was so nice because it was right on our chart. This one's a little bit tougher. So I'll start off with this is 1 over sine of 5 pi over 3. And I'll first guide you through this the way we've been. I'll change this into degrees. The pi is 180, so I end up getting 1 over sine of 300 degrees. This is what I was talking about, everybody. The angles are not the question. We need to be able to do that work as necessary. The problem still comes back to knowing the trig function at that angle. Whether you're looking at it in terms of radians or degrees, that's not the part of the problem. It's evaluating the big picture here. So sine of 300, well, now I'm in the fourth quadrant. I'm bigger than 270, I'm smaller than 360. So that represents my 300, and there's my reference angle. That would be 60. 360 to complete the circle. I'm coming short of 360. 300 is short of 360. How short? 60 degrees short. After a little while, a lot of people can do this thinking in their head, but especially if you're a little out of practice or it's something that you haven't been as strong with, it's a good idea to draw the picture to help guide you. So now, coming back, I've got 1 over. Well, I'm in the fourth quadrant. Sine is negative in the fourth quadrant. The angle is 60 degrees, and sine of 60 is radical 3 over 2 from our chart. Cleaning this up, not as bad as this one. Here I had to do some real division. Here this is one of our 1 overs, so it just flips. And again, everybody, I really don't mind if you leave your answer like this, but the book will always rationalize. So the book would write that. Multiply top and bottom by radical 3 to get the radical to cancel in the denominator and end up with negative 2 radical 3 over 3. Okay, I want to do 2 more here. And all of these, everybody, these are the warm-ups. We're going to do all this to get one problem at the end to just get a little more practice as far as what we're going to need moving forward. Because all these trig values, all these trig functions are functions, so we would just want to connect it back to our f of x, our function notation. So 2 more. Let's next do secant of 180. Well, secant is 1 over cosine, and this is, oh, I'm very sorry, everybody. Let me go backwards for 1 minute. I said I wanted to show you how to do this in radians as well. And everybody, it's really the same thing. All the way around the circle would be 2 pi. So in the same way 360 minus 300 gave you the 60, I would do 2 pi minus 5 pi over 3 to figure out the reference angle. Do a little work. This would be 6 pi over 3. Treat it as 2 pi over 1. Get your common denominator. 6 pi over 3 minus 5 pi over 3 equals pi over 3. So I'm still in the fourth quadrant. 5 pi over 3 was bigger than 3/2 pi, smaller than 2 pi. I knew I was in the fourth quadrant. Sine is negative in the fourth quadrant. But now instead of 60 as my reference angle, I have pi over 3. But again, same thing. I'm still getting sine of that angle gets me to the rad 3 over 2. Oops, sorry. Sine, either way, pi over 3 or 60, gets me to the rad 3 over 2. And I'd still have to clean up that answer a little bit. So it's not that terrible. And the more you do it, the more you'll start to realize, just drop this number. As long as the fractional part is reduced, 5 pi over 3 will have a reference angle of pi over 3. 4 pi over 3 would have a reference angle of pi over 3. 2 pi over 3 would have a reference angle of pi over 3. As long as the fraction is reduced. So if you had like 6 pi over 9, well, 6 over 9 reduces to 2 over 3. But as long as your fractional part is reduced, pi over that denominator would be your reference angle. That's not a coincidence. So, okay. Again, nothing wrong with thinking in terms of degrees, just pointing out radians. You're basically doing the same thing. You're still thinking about comparing to the quadrant boundaries to know what quadrant you're in, and doing a little bit of that work to figure out your reference angle, and then coming back to the chart. Value from the chart combined with the plus or minuses that you got from the quadrants. Okay, so now back to this one. So we had secant of 180. We wrote it as 1 over cosine of 180 because secant is 1 over cosine. And now we hit our first little hiccup. If I really try and do this problem the same way I've been doing all the others, I run into a little bit of a stumbling block because 180 is the boundary. I'm not in quadrant 2, I'm not in quadrant 3, I'm on the boundary between them. So this is where the unit circle pays off some big dividends. If we know the unit circle, all I need to know is 180 is here and cosine is x. So therefore cosine of 180 is -1. That finishes the problem. 1 over cosine of 180 is -1, and we'll just clean that up. 1 over -1 is -1. But if you need to do it this way, it's just a little bit harder. You'd say to yourself, well, I'm between quadrants 2 and 3. Well, it doesn't matter. Quadrant 2 or quadrant 3, cosine is negative, so we get the negative part. And then what's the reference angle? The reference angle is the angle to get back to the x-axis, but we're on the x-axis. So we would use a reference angle of 0. So I get the value from the reference angle and the plus or minus part from the quadrant. You just got to stretch it a little bit. The reference angle is a little weird if you're on a boundary because it's either 0 or 90, but those are on our reference angle chart. But now, again, just you have to think about the two quadrants. If I want to know about cosine down here on the boundary between 3 and 4, well, cosine is negative in 3 and positive in 4, so I must have a 0 to have a sign. Remember, 0 has no sign to kind of balance out your in-between signs. So a couple ways to think about it, but if we know the unit circle, the boundary problems are even easier because we're always just getting the 0, the 1, and the -1 for your appropriate x or y, depending on if it's sine or cosine and which boundary that you're on. So last one here, number 7. And then number 8, I'll just do a slight flip, getting us into the function notation. Problem number 7, let's consider, let's do another secant. Let's consider secant of 570 degrees. Okay? Actually, no, I'm sorry. Let's do a cosecant. Sorry about that. Let's do cosecant of 570 degrees. Well, cosecant is 1 over sine, but 570 is too big. So I'm going to use a coterminal angle. I'm going to subtract 360 so I could figure out what quadrant I really am in and to figure out what is my reference angle. So this is equivalent. Again, just like up here, whether you're converting or down here, I'm doing this work with reference angles. If my given angle was negative, I'd add 360 to make it a standard angle, get it in that nice interval that we like. But this is not solving the problem for me. It's just retranslating it. 1 over sine of 210, and now we can handle that. We know how to handle sine. 210, well, 210 is here in the third quadrant, so that would be 210, but I need this reference angle here. Well, realize reference angle is always going to the x-axis. This time I'm going past the 180, so I do 210 minus 180 to get the reference angle is 30. I'm in the third quadrant, so I know sine will be negative. Negative what? Well, at 30 degrees, sine has a value of 1/2. So 1 over minus 1/2 would give me an answer of -2. And now this very last one. And again, all this is good information we need to know, but there are no test or quiz problems from this. Understanding these ideas is what's going to allow us to use these in some slightly more complicated situations, and also when we start solving equations, we'll kind of do some of this work in reverse. So the last one here that could show up on a test or a quiz will have a slightly different form. Given f of x is cosine of 2x plus 4 sine x plus cosecant x. All of that is given information, and we're being asked to find f of pi over 6. Function notation. Plugging this in. Now, I'm giving it to you in radians again. If you want to do degrees, no problem. But still, plugging in the x to then find the y. So I'm going to plug in a bunch of trig functions, and then I'm just going to do all the arithmetic to combine my answers at the end. But when I plug in, I really want to emphasize there's a very big difference between having a multiplier inside with your angle versus a multiplier out in front. So let me do it here with 30 degrees. If I plug in the 30, inside, order of operations, do what's inside the parentheses, 2 times 30 is 60. So I'm actually going to find cosine at angle 60. But in this next part, the 30 gets plugged in, and this 4 hangs out in front. And then I also get the cosecant of 30. But now I go to do my work. Well, here, cosine of 60. I was at least nice here. All these are in the first quadrant, so I'm really just going to my chart. Cosine of 60 is a value of 1/2. This 4 just pushes along, and sine of 30 is 1/2, and the cosecant is 1 over sine, so that'll become a 2. And I'm sorry this is getting blurry. Just to finish this arithmetic, 1/2 plus 4 times 1/2 is 2, plus 2, 1/2 plus 2 plus 2 is 4 1/2, or 4.5.